All right, good morning, everyone. I'm Nishant Garg. I'm an assistant professor at University of Illinois. Very glad to be here and talking a little bit about nucleation seeding. And I think I must thank the previous speaker who did a good job of explaining about seeding, so I won't spend a lot of time on it. So let's get started here. And I see a lot of students in this room, and one of the things I know students communicate best via memes, so I'm going to start with a meme. so I hope I don't offend anyone, but I hope you have seen this meme. It's pretty common, right? And you have this situation where the one spouse is thinking, I bet he's thinking about other women. And if you're working too long on this low carbon concrete, how can I improve the early strength of my system? And I want to be very clear here that when I mention low carbon concrete, I'm talking about high SCM concrete. I'm not talking about other chemistries, CSA or so on, and even if you make Portland cements with some other process. So it's really high SCM concrete I'm talking about. If you add a lot of SCMs, you dilute the clinker, you dilute this powerful A-light phase that gives you the early strength. And when I talk to my friends in the construction field, and for them, schedule is everything, right? So we have to solve this problem. If anybody has a solution, I think that'll be big. So if we start off with looking at the scale of this issue, right? If you have macro, micro, and nano, right? Macro is what happens in the field. Micro and nano is maybe some of us care about a lot. Cement is really a micron-sized kind of a spice, is a mixture of many spices. Nano, I haven't put a picture here because it's hard to see the nanoscale with your eyes, but I promise there's some TEM images of the seeds I'll show at the end. But I'm going to start a little bit with the micro because this is something we have been doing quite a bit, and I think there's a lot of room here for optimization. Right? So let's talk a little bit about this technique called Raman imaging we have been working on. And essentially, what we do here is we start with an optical image, but at every point, we take this kind of grid-like pattern, we get a Raman spectra, and that Raman spectra can be assigned to a phase, and you can get, in this case, it's a granite rock, and you can get the spatial distribution of all the phases. Okay? And I should tell you, right, I'm in the middle of teaching a semester large course to undergrad, so I'm going to ask you some quizzes because I want to keep it interactive, right? So let's look at a Raman image of a common material, and I can bet that many of you in this room have put this material in your mouth at some point. So can you guess what this material is? So here Tylenol, so it's really an Excedrin tablet. You can see there is aspirin, Tylenol, and caffeine. So the pharmaceutical industry already does this for quality control. This is a cross-section of a pill. You can not only quantify the key phases that are present, but you can see the spatial distribution, right? And you can imagine if they had bad quality control, and all the caffeine was on the right side, and if you were somebody like me who likes to break the tablet in half and only eat half of it, I'll be just high on caffeine and not get the Tylenol, right? So the idea here was, can we use Raman imaging, this approach on cements? So this is exactly what we've been doing. We make this little pill. This is cement embedded in epoxy. We obtain this very high resolution Raman image. Each of these composite images have 250,000 pixels in it, so we have statistically large number of points to reliably quantify things. So we get pretty good correlations with XRD on a variety of cements. We did 10 different cements from the US. And what we can then start to produce are these individual maps of phase. It is a map of A-light, and we can start to see the individual A-light trains if you zoom in. It's like a Google map, but you can zoom in to a very high level. And then you can obtain all these phases for all the different things that exist, even down to things like quartz, which is really an impurity in the cement, right? This is the unreacted ingredient, but you can now see it. Okay? Another quiz, and you will get bonus credit at the end of the class. What phase is this? So it's a bit of a tricky question. This is not really a phase. This is an iPhone photo of the night sky my student took. And we're doing the same thing as astronomers do, right? We're just counting the white pixels. In this case, these are stars. But in our case, these are the stars of cement, which are the clinker phases. What else can we do with it? We can actually get now the size and shape of individual clinker phases, right? So here's again a high-resolution Raman image where we can see all the phases in their glory at different magnifications. But now if we do a quantitative analysis on this, we can get the particle size distributions of each individual phase that is present in this system, right? So if you take this, what we call these are the phase-specific PSD. So instead of having a global PSD, you have a PSD of every single component in it, right? So you can imagine if you have type 1L cement, which I hear a lot of people are talking about in the past few years, you could have two type 1L cements with the same amount of limestone, but depending on how they're grind or ground, the fineness of the limestone within that could be different, and that would affect your strength, water demand, and so on. So with this, of course, you can get all sorts of statistics. You can get the shape parameters, the volume fraction, and then what we did last year was we had this paper out in JPCC where essentially we get the size distribution of these phases and try to relate them with performance. So in this case, I tried to explain this to my kids because I was making this slide and they were just hovering over me. So I said, cement is just like a box of M&Ms, and one would imagine all these M&Ms are essentially of the same size, even though they're different color, different phases. But in reality, they're all of different sizes and shapes and all randomly distributed. And if you take all of that into account, you can build what we call this the composition size quotient, which takes into account not only just the composition, but the individual size distributions of all the phases, and then you can reasonably predict the 3-day isocal heat on a variety of 10 different cements. Right? So I think this is kind of a starting point where we can take this technique forward, and these very high resolution images become an input to a model which can predict performance very well. Right? The global PSD is not enough. We need the phase-specific PSDs. All right, I come back to the nano, right, which is the seeding part here. Let's look at the CSHC's prevalence in literature. So I did this kind of fun exercise. I just did a Scopus search on how many papers are out there on the CSHCs, and you will see this kind of an exponential trend if you think the field is becoming a little bit hot. Right? So there's about 60 papers in the past few years per year. But of course, you have to do this exercise carefully because the total number of papers are also increasing. Right? So let's look at how many cement papers are being published. Any idea how many papers with the title cement are coming out every year? 3,000? We can play Price is Right. It's actually about 30,000. So just a factor of, so this is the cement publication. So then what you should do is you should normalize the CSHC publications with that cement, right, to really see if this is increasing. I think there is a bit of an increase, and that means people are looking into it. And if you look at the dose percentage here, 0.2, it maybe correlates a little bit with the dosage that some of these seeds are being used for. Okay, one thing is, any idea what's happened here in 2010, which is starting this? So what I think my hypothesis here is that I think this is where one of the patents from Luke Nicolau was, I think, filed in 2009, and I think that started off things. There's an obscure paper in the 1980s you can find on CSH seeding, but I think that's talking about something else. That's not really the seeding we are talking here. Anyway, so what we have been looking at is this commercial product, Master X seed from Master Builders, and we have these 3 questions we wanted to answer. And as you read this question, I want to just frame that this was specifically done for the DOT, Illinois DOT, and they were interested in opening their pavement and so on early to the traffic, and they wanted the early strength. And we said, well, let's maybe explore the seeding and how that can work. So I'm going to show you some results which are very practical, so bear with me. The other thing we wanted to do is, if you look in the literature, the X seed sold in the US versus the X seed sold in the Europe is under different trade names. I don't know why. I think there's probably some complicated history of patents and reorganizations there, because the companies have also gone through a lot of reorganization. But we want to know the US X seed products, how do they work? So we went with this kind of very standard lab testing protocol and some field testing, and I'll also show you some field implementation where we implemented some concrete with these seeds in a box culvert in Illinois. If you look at the kinetics with isocal, again, you see a very standard trend which agrees with literature. Depending on the dosage, you see this kind of increase in the hydration as well as a little bit of acceleration. Right? And again, this is expected. If you look at the cumulative heat, the rise is around maybe 40 to 50 joules, which is about 10 to 15%. Then also the other thing is, if you look at the 2 admixtures here, and the interesting thing here is that the 2 admixtures also kind of behave a little bit differently. One of them seems to increases things, accelerates things, and one of them seems to slows down things. And I just want to be clear, I'm not talking about the US election, I'm talking about admixtures. And that's all I'll say about that. All right, if you look at the Exceed 44 and Exceed 55, again, you have kind of slightly different behavior. One of them is accelerating the reaction, one of them is a little bit retarding. And one of the reasons, again, you have quite a bit of high-range water reducer, and I think that's causing the early retardation. But if you look at the cumulative heat in both of them, it's actually improved. So in terms from a strength point of view, both of them work. It just depends on how much workability enhancement you need. And that's where I think you could have one or the other as a beneficial. There's also application in precast versus ready mix. in looking at the strength, again, generally strength increases, but then what we've been also interested in looking at the durability side, so measuring open porosity through helium picnometry. And again, you can see that there's a drop at the first few percentages, but later on the porosity kind of stabilizes. About 1% dosage or so, you get this few percent decrease in porosity, which is nice because then you also have a little bit of a durable or impermeable system. The other thing we have been also looking at this with a little bit of a blended system, and again, adding a 2% CSH, you do see this decrease in porosity for different systems, which I think is also then evidence that some kind of refinement is happening. And this is all available in this report that came out last year. Okay. Then one of the other things we also were very interested to see, and this is something we are developing in the group, to use laser profilometry to look at the roughness of the samples. And the fascinating thing here is you're finding that if you do this in a large enough area and quantitatively, the roughness that you get from laser profilometry actually somewhat correlates to the porosity in the system, right? And again, this is still work in development, but I think there's a lot of potential here. If you have a laser profilometer, it's a very, very nice tool. And what we have seen here is that if you look at some of the laser profilometry parameters, which is such as the peak curvature as well as the number of peaks per unit area, it actually has some correlation with the open porosity you get from helium picnometry. And for somebody like me who does a lot of characterization, if I see some kind of correlation between two different techniques, I think there is something happening there. So I think there's a lot more we need to investigate, but definitely there is some chance to kind of explore this technique for characterization. There is this paper in 2023 with my student Hussein Kabir, and we go into quite a detail about how this works, so you can take a look. All right. Looking at some correlations, again, just to see for all these, now this is at the concrete scale, I mean for lab and the field scale, you see generally many of these things talk to each other. DOT again was also interested in looking at the formation factor and the resistivity results, so we did that on the concrete cylinders. And again, generally we see there are these correlations which we would expect generally. If you look at specifically the formation factor versus compressive strength, this was kind of something interesting. If you look in the lab, you get almost a linear correlation, but in the field, it's kind of all over the place. So because one of the things they wanted to check is, can you use this to predict strength? And I'm like, that really bit depends on really the mix, because in the field now you're having a cocktail of admixtures and many other things that influence, so it may not be a one-to-one. In perfect conditions in the lab, you can have that, right? Okay. Talking about the field implementation, so we put this Armstrong in Vermilion County. We picked this project. Again, the DOT was very interested to try this, and we find again with the CSH seeds, they were able to get this kind of bump in the strength, and I think this is what was kind of really important. When you have this kind of a bump, even though it's kind of on the order of 15 to 20%, it can help with that early opening of the pavement. All right, so as I promised, I will show you some TEM images, and this is something I just got a few weeks ago. I want to just say I want to show a picture of the seeds because there's not so much out there. And again, depending on what you use, you do kind of get to see this almost on the order of 100 nanometers or so, little particles suspended in a PCE. And if you kind of zoom in again, you kind of see this kind of almost like amorphous CSH gel. And when we compare this with some of the CSH gel pictures posted by others, it more or less matches. Okay, so just to summarize what we have talked about here, the CSH generally can affect the kinetics, so it depends on dispersion medium. You have to be careful about how much PCE is there, because that could retard things, but generally the overall cumulative is improved. Based on helium picnometry and laser profilometry, there is now good evidence that these are refining the microstructure. Finally, we did implement this in the field, which does prove their efficiency, but I should be cautioning you at the end of the day, the improvement is on the order of 15 to 20%. If you're looking for 50%, 70% improvement in strength, you do need something a bit more potent, and this is where maybe alkanoalumines and some of these other admixtures could play a role. But for these, at this level of 15 to 20% increase, they reasonably work. So what we are now proposing to that kind of picture of improved hydration is that, yeah, of course they improve the hydration, but they also refine the microstructure a little bit. So if you're concerned about durability, the seeded mix have a role. The other thing you could also consider is that if you want to lower down your cement content, again by 10%, 15%, you can have that mix with a slightly lower GWP and add some seeds there. So that is all straightforward. I think at the end of the day, it also depends on the kind of cost of these admixtures and so on. So if those economics work out, then this is a potentially good solution. Okay, so with that, I want to thank my team and specifically the students. So this is Faisal, his PhD student, and this is what he's been working on. And you can find his papers online. And I also want to thank the Illinois DOT as well as ICD for supporting this work. And I'm happy to take any questions.